Okay, so pretty heavy talk this one, lots of math. That's why I recommend you bring your pen and paper. You want to ask me a bunch of questions. We're basically going to speed run through 3 chapters of the Sutton and Barter textbook because I assume by default you know nothing about reinforcement learning. Great, let's go. Okay, so what is reinforcement learning? So up to this point we've been in the supervised learning regime. Everything's nice and easy. We have access to labeled training data. We have a nice loss, an objective measure that we can differentiate and backpropagate through. So I get a clear measure of boo, you suck, and here's the direction you should go to get better. The agent only sees the real world once it's been trained for a while and then deployed. We assume that the data is IID, independently and identically distributed between batches. So that is if here's a batch of data and you make some Garbo predictions, don't worry, here comes the next batch. Future decisions aren't predicated on decisions in the past. Everything's nice and independent, which means you don't have to do any planning when it comes to supervised learning. RL, throw it all out the window. RL is a whole different ballgame. So a few problems with RL. The only feedback that you get is a single scalar number. You get the carrot or you get the stick. That's it. So first problem, sparse reward. If I'm training a bot to play chess, a natural reward is a 1 if you win and a -1 if you lose and 0 otherwise. So suppose you've never seen the game of chess before and I sit you down in front of a chessboard and you don't even know the rules of the game. You sit there and blindly make moves, and as soon as you make an illegal move, you get the stick. As soon as you lose the game, you get the stick. And if by some miracle you manage to win the game, you get the carrot. It's going to take a long time to learn from this sort of feedback, right? Probably literally billions and billions, or probably I don't know, thousands or millions of games until you learn the rules of the game, and probably many billions of games after that before you actually get reasonably good. However, this seems to work. AlphaZero was trained more or less in this fashion, and it got to superhuman from just the carrot and the stick. So I don't know, a billion years of subjective torture and you two can get good at chess. Reward attribution, what action mattered? Suppose by some miracle you won the game, which move along the game was the critical juncture between a win and a loss? It's it's not clear. You have to sort of work out for very limited feedback what matters and what doesn't. So attributing reward to good and bad things is difficult. It's you train a pet and you give it a treat when it does something good. The pet has to work out what's the thing that I did in that long sequence of moves that got my master rewarded me for. It's not easy, right? No ground truth. Optimal policies unknown. I don't even know how to play chess very well, let alone what optimal play looks like. So it's often hard to get a measure of what's good and what's bad without some other measure to compare against. And we also have what's called the explore versus exploration trade-off. So the agent, by default, doesn't even know how the world works. So he's got sort of 2 competing goals. Do I take random actions to sort of explore how the world around me operates? Or do I try and exploit what I believe the world to be to try and milk the most reward based on my current beliefs about the world? So there's this perpetual trade-off between exploration and exploitation. And often, the RL agent is online only. So it's not we train for a while and then deploy. The agent is then born and then booted into the world. It's all right, go work it out. And it's got to on the fly try and learn how the world works and then try and milk reward from it. So RL in general, very different ballgame from supervised learning. Questions so far? I said a lot of words. Cool? All right. Okay, here's a slide that I knocked off from Jan LeCun. He describes RL as the cherry on top. So basically when you train something like a big LLM, self-supervised learning is the entire cake. So this is you throw in just anything and everything, big scrapes of data from the internet, and the model just gets good at predicting next token. The icing on the cake is the supervised learning. So this is your very high quality curated question answer data set to make the model be a chatbot or whatever. And the little cherry on top is the reinforcement learning step at the end. So this is training the model to do things that make a reward function happy, or do things that make human evaluators happy, which makes the model I don't know, be good at helping you, but not tell you how to make a bomb. Question over here?
I guess with the new reasoning paradigm, this cherry is getting very big.
The cherry, yeah. So this slide probably should be a little bit updated, and the cherry is a bit bigger and the icing's not so big. So maybe the modern regime is a cake with a whopping big cherry on top, because we just do lots of R from scratch. But today is only cherry. We just only learn from scalar feedback. There's no data whatsoever. You just got to learn from the carrot and the stick. Back in 2016, 17-ish, when we trained models only with RL to get good. Does anyone see the OpenAI hide and seek stuff? The little guys running around? Only cherry. No other feedback was given, and they got really good just from that. Downside is, it takes a long time. If you were to train an LLM to learn how to predict the next token just from scalar feedback, it would take ages just to learn grammar and vocabulary, let alone anything semantically meaningful. So in practice, what you normally do is bootstrap up from data and then afterwards do the cherry on top RL stuff rather than cherry from scratch. But if you don't know anything about the world, you don't have any training data, then cherry's all you got. Cool. Questions about that? Yeah.
Did you say cherry one more time?
Cherry. All right. Cool. This goes in the recording, mind you, so now Jolly's going to have to cut that out. Okay, cool. Cherry learning. Okay. Multi-arm bandits is the simplest kind of RL environment. Basically, the agent walks into the casino and there's a bunch of like slot machines called one-arm bandits because they've got one arm and then they take your money. There's an unknown distribution for each slot machine. So I've got a set of actions. I go up, I pull the arm, and then the slot machine spits out some money sampled from some distribution that is like unknown to me, but conditional on the action that I chose. On time step T, I choose action AT, and I receive reward RT sampled from the machine as a function of which action I chose. Obviously, the thing I want to do is just find the machine with the best expected payout and then just always play that machine. But I don't know how the machines are distributed. I got to like sit around and play all the different machines to get a vibe of like how much money they pay out and then balance, do I like try random actions to explore more or do I attack what I think is the best machine and only play that one instead? So this, even for a simple setup like this, where there's no interaction between past and future, if I play a machine and it sucks, I can always pick a different machine. I can never get trapped into like stuck in a hole or something like that, but I can for MDPs, which we'll see in a moment. Already we have like an exploitation versus exploration trade-off. So we need to balance exploring versus doing good. Cool, cool? Okay, so the first simple, okay, so here's an example I knocked off from Sutton and Bardo. You have 10 slot machines. Each of them has like a Gaussian distribution. Obviously, if I knew this picture, I would just always play arm 3 because there's the highest expected payout, but I don't, so I have to somehow learn which arm is the best and then play that arm. Okay, so I have an estimate of the reward of playing some arm at the time T. My best guess is up to time step T, how many times have I played that arm, which is going to be the denominator, and the numerator is the sum of all rewards received from that arm. So this is like an empirical estimate of the mean, of the expectation of the reward from a particular arm. So I log this for every single arm, and the most naive thing I could do is I always play the arm with the current highest expected payout. However, this is a bad strategy, because often you can get stuck with a suboptimal arm. So by default, I believe all the arms are worth 0. I play one arm, I get $1 out, I'm like, oh wow, fantastic, this is like the highest expected value. And then I keep playing that arm, and let's suppose it only pays out like between 0 and $1. Then the expected value of that arm will always be positive, but maybe there's another arm that pays out $100, but I'll never try it because it's not currently what I believe to be the best. So this strategy, a greedy strategy, doesn't explore very well. You immediately get stuck. That's not good. Questions so far? Cool, cool. Okay. So what else can we do? First thing we do is just every now and again do random stuff. So this is called an epsilon greedy strategy. You flip a coin, a biased coin, and if the coin comes up heads, you pick a random action in general. If the coin comes up tails, then you pick what you think is currently the best arm. This does converge to like always picking the best arm 1 minus epsilon of the time, but you can imagine it's like not a very good thing to do. If you like play an arm and it's like really, really bad, you probably don't want to randomly explore that one again. We really want to explore stuff that I like. I want to pick actions that like I know are good or that I don't really know much about. I don't want to do things that are like bad and I know that they're bad. That leads us to our second quite nasty equation, what's called upper confidence bound, or the UCB algorithm, which is split into 2 parts. So the UCB algorithm, the arm that it chooses is either we have the best current estimate of how good I think that arm is, and this is just, again, the like empirical measured mean for that arm. And then we have a nasty looking exploration bonus here. What's the motivation between the exploration bonus? We have on the denominator the number of times I've tried that arm so far. If I've never tried that arm, divide by 0, exploration bonus is infinity, I'll always play it. So the first thing the UCB agent does is it tries every arm once. That seems reasonable. And then what else is going on here? If I've tried an arm lots and lots of times, the denominator is very big, then that means the exploration bonus is quite small, and I'll only play an arm if it's good. So the only arms that don't get chosen are the ones where this term is low, I believe they're bad, and this term is low, I'm confident that they're bad. So I only want to do things that are good or I don't know anything about, I want to learn some more stuff. The stuff in the numerator, grows logarithmically. This is just like a little fudge term. So like theoretically, you can derive this like asymptotically converges. And there's an extra hyperparameter here, C. If C is bigger, it wants to explore more. If C is smaller, it wants to exploit more. 10 pages of math will tell you that in the numerator, natural log is best, and the constant C equals 2 is best, that I will not cover. But if you like, you can have a look at the whole textbook on bandit algorithms. It's like 300 pages long. We will take it on faith that 2 is best and natural log is best. Intuition behind this term here, this kind of sort of looks like the variance of the arm. So essentially, our best guess of the value of the arm is like the mean plus something proportional to the variance. So it's like an optimistic measure. It's an upper bound on how good the arm is, ergo upper confidence bound. Cool. That's basically like bandit solved, easy peasy. Anyone got questions about that? Yeah. Assuming some niceness conditions in that like the arms, the reward distributions for the arms are like I think Gaussian or at least have like well-defined mean and some other niceness assumptions, yes, this is optimal. Anything else? Okay, cool. That's UCBs. Okay, so next problem is if we're interacting in an environment that's got state. So maybe like it's a casino, but if you pull an arm, maybe something else happens that affects the distributions of other arms, or if you like exploit a particular slot machine too much, I don't know, you get thrown out of the casino or something like that. So now like the environment has history, it has memory, what options are available to you in the future depend on what happened in the past. So we formulate this as what's called an MDP, a Markov decision process, which is defined as a 4-tuple star, a finite set of states, configurations in which the world can be, a finite set of actions, things I can choose to do, a transition distribution, which is, as far as you're concerned, a great big matrix lookup table is what we'll use today. It's basically a function that, given a state where you are, and given an action, what you choose to do, gives us a distribution of all what the future states look like. For today, we will assume we have access to T and solve directly, but in general, you can't see T, you have to learn from experience. We can interpret T as basically the probability of the next state being S prime, conditioned on the current state as S, and the action I chose was A. And we also have a reward function, which is just a deterministic function of where you are, what you did, where you went, and it spits back a number for like the carrot or the stick. The only thing the agent ever cares about in this world is like reward go up, and we'll do whatever it can to make that happen. Any questions about this framing that I've given you?
You said reward.
Yes.
Deterministic.
Yes.
Non-deterministic.
No, I mean deterministic, but because there's like noisiness in the transition distribution, this rolls into noisiness for the reward. One can frame MDPs as the rewards also being non-deterministic, but it's no more expressive because you just like add extra states. So if like the reward could be a coin flip, well, I just add like a head state and a tail state, and the reward's just deterministic. So this restriction makes the math a bit easier, but is no less expressive. Cool. Anything else?
Yeah, sorry, once again, you say that it's a state times action times state? Because
Yeah, it takes in where you are, what you did, where you went, and you get a reward for doing so.
Okay.
Cool. Okay? Cool. Okay, the agent has a policy. This is how it chooses what to do. So the agent is a function given a state. Give me a distribution of actions. Yes, question?
So what's the delta symbol?
The delta symbol is a probability simplex, which is, this is the set of all distributions over actions. So given a state, I will give you a probability distribution of actions. And given a different state, I will give you a different probability distribution. If you like, you can think of this as just returning a probability vector with a number for each action that like, you know, they're all non-negative, they sum to 1, blah, 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 blah. That's how we'll encode it for today. Cool. Okay, anything else?
So those are like it's like a soft max kind of optimal.
For when we do it with neural networks later on, yes, it'll be some like spit back a logit vector and softmax it, yes. But not for today. Yes.
This is the policy at a point in time, right? The agent can change its policy.
Yes. So the policy is a function only of state, but like the optimizer can change the policy. Okay? Cool. So one can interpret the policy as the probability of the agent choosing action A in time step t, given the currently standing in state S at time step t. Happy so far? Okay. These two things interact together. So on time step t, the agent samples and the agent looks at the state that he's in and samples an action from his policy, gives the action to the environment. The environment does whatever it does and samples back a new state conditioned on where you are and what you did. It feeds that new state to the reward function, which is where you are, what you did, where you went, and spits back the carrot or the stick, some scalar feedback. And the agent receives back the new state and some reward as feedback for whatever the new state is. And then we just loop this for either some finite number of steps, or we loop this for infinity. So we generate what's called an interaction history or a trajectory. You start somewhere, you do something, the environment gives you feedback. Then you do something else, the environment gives you feedback, blah, 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 blah. The two parts sort of like interact in this loop in this way. Cool. That's like the framing for reinforcement learning. This macro decision process is the world in which we'll be interacting for basically the rest of the next few days. Anyone got any question about the notation that they'd like me to talk about? Cool, happy so far, excellent. Okie dokie, that's an MDP. What's the objective of the agent? The objective of the agent is to maximize the sum of all future rewards. So in the time step t, I'm going to maximize all the rewards from now to infinity. Few problems with this framing of maximizing the return. For an episodic environment, so you live for capital T time steps and then you die, this like sum is always well defined because there's only finitely many rewards, the rewards are always bounded, and a finite sum of finite things is finite, so no issues there. Issue is for continuing environments where like the world never ends, this sum might diverge. So if I give you the reward sum 1, 1, 1, 1, 1, 1, or the reward sum 2, 2, 2, 2, 2, 2, presumably 2's forever is better than 1's forever, but they're both infinity. I can't really compare infinity to infinity. Second problem is the agent might be lazy. If I like sleep for 1,000 years and then play optimally, get it 1, 1, 1, 1, 1, that's the same as if I played 1, 1, 1, 1 reward from the very first time step. Again, infinity to infinity, I can't really compare, but presumably not being lazy for 1,000 years and then playing optimally is worse than playing optimally from the very beginning. So we need a way to compare these two things. The environment is stochastic, the rewards are often up to chance. It needs some way to compare like unlikely big yummy reward versus like very likely small reward. And I need a way to like trade off from now to the future. So would you rather $100 now or $110 in a year's time? I mean, I don't know, it depends on like your value of money, I guess. So the way that we solve these problems is we use what's called a geometric discount. We had a discount factor gamma such that the reward now plus gamma times the next reward, plus gamma squared the reward after that, and so on and so forth. This is a geometric sum. Convergence is guaranteed, even if the sum's infinite. Hooray, that's nice. And then we want the agent to choose actions that maximize the expected value of this, because we don't know precisely what the rewards are going to be, because the environment's like kind of noisy, and or we don't know precisely how the environment works a priori. Cool. So this is the thing that the agent wants number go up, all else is secondary. Questions about this? Yes.
Wouldn't this lead to some greedy behavior? Because the reward in the next day is better than maybe a bigger reward on men.
Depends how you tune gamma. We'll see this in the next slide.
Okay.
Yeah. Any other questions? Yeah.
Could you not have an environment where you're expecting the rewards to increase over time such that this doesn't converge?
There are finite states, finitely many states and finitely many actions, finitely many state action state triples, so finitely many rewards, the rewards have to be bounded. Cool, okie dokie. MDPs are the following nice properties that we will exploit. First, stationary. The environment doesn't change. Once you've learned it, you can exploit it forever. This means data from the past is just as good as data right now. The Markovian, obviously, so the distribution only depends on the current state. That means, in principle, you only need to see the current state to play optimally. If you're like playing chess or whatever, and I like dump Magnus Carlsen halfway through a game, he could probably still play pretty well from that point, not having seen what happened before that, because it doesn't actually matter what happened before that, you know, modulo castling or whatever. But assuming you've like you've been told whether the board's already castled or not, you can look at a current board state in chess and know how to play optimally from there if you're like really good at chess. You don't need to know the history that led up to that point, because the current state of the board tells you all there is to know about the world. The history that got there is irrelevant. The history that got there might be relevant for the optimizer for learning, but it's not relevant for once you've learned the optimal strategy. Okay? It's fully observable. In general, this is not true, but we'll make the assumption today that looking at the board tells you everything there is to know in the world. An example of something that's not fully observable is like poker. I can see my hand, but I can't see your hand. So I have only like a fuzzy, partial observation of the world, which means I have to sort of like infer what I can't see. Whereas in chess, you see all there is to see. The reward hypothesis, which we're implicitly assuming that any kind of goal or any behavior I want to incentivize can be communicated with the carrot and the stick. The entire field of reinforcement learning rests on this maybe somewhat tenuous assumption, but we're going to assume it because that's all we've got. Cool. Questions?
Could you rephrase the reward hypothesis?
Sure. Basically, any sort of behavior or goal that I want to communicate to you, I can achieve by just like scalar rewards, just like the carrot and the stick. Any behavior I want to train my pet to do, I can do so with like positive and negative reinforcement. Cool. Okay. All right. So we want to define the goodness of a state. So the agent wants to bring itself towards states that are good and avoid states that are bad. The value of a state obviously depends on whatever policy you're doing. If you're near the end of the game and it's almost checkmate, but I'm a really bad player, from my perspective, this is like a bad state to be in because I'm like too stupid to see the move that wins the game. So it depends not only on the state, but what your current strategy is. The value function, as a function of your current strategy pi and the current state s, is the expected value of the return from here to infinity conditioned on we're in the current state s. Implicitly, this expectation is also with respect to the environment's transitional distribution t. However, because the environment is stationary and doesn't change, but the agent can change their policy, we just like leave the t out for the expectation. But implicitly, remember, it's with respect to both what the agent is doing and what the environment is doing in response. Okay? Cool? Okay. So now we're going to express what's called the Bellman equation, which is like basically the core equation in reinforcement learning from the value function as defined. So we judiciously note that the geometric discount allows us to factor the return in this way. I can write the return from here to infinity as the very next reward plus the discounted return on the next time step. We can then define the value function in this recursive way. So here's just the definition of the value function. We substitute in the next reward plus discounted value of the return. We can then factor this because expectations are linear, so they distribute over addition and they distribute over scalar multiplication. And then here's the scary step. I'm going to slow right down. Whoa, what happened there? Okay, so let's stare at this term here for a moment. The expected value of the very next reward. What's the very next reward going to be? First, consider all the actions that I could have done and how likely those actions are. So sum over all actions A weighted by how likely my policy would have chosen them. And then sum over all future states S prime, how likely is it that if I was an S and I took action A, the environment responds with state S prime. This is like sort of like a tree brute force of all future paths, but only one step into the future. All the things I could have done, all the things the environment could have done in response, multiplied by the reward I got for doing so. So sum over all paths of like where I am, what I did, where I went, how likely it was I got there, how likely it is I took the action to get there, sum that all up, that's the expected value of the very next reward. Yeah, happy so far? And we do the exact same argument for this term here. Leave the gamma out the front, sum over all the places I could have went, sum over all the things I could have done, all the places I could have gone, the expected value of the reward of the next state conditioned on I'm now in state S prime rather than I'm in state S. This looks suspiciously like the definition of the value function, but one time step into the future. Yeah? Cool? So therefore, I can replace the value function here, and now we have an equation that describes the value function in terms of itself. This is like the core equation of reinforcement learning called the Bellman equation, which I have here on the next slide. Hooray! So if you look, this is in fact a linear function for the value of every state. And we know how to solve linear equations, right? It's like big matrix map mul, do the inversion or whatever, right? So given a policy, I can work out, sorry, where are we? Yes. Given a policy, we can work out the value for every state by just solving n sets of simultaneous equations where n is the number of states. If your policy is deterministic, this reduces even further because you don't have this extra summation at the front. Maybe it's worth we like stare at this for a moment while someone asks me some questions about this.
So was the value function independent of t?
Yes, the dependency of t drops out. And that's only because we use a geometric discount, which is like a time-independent discount. $100 now or 110 bucks in a year is the same value proposition as 100 bucks in a millennia or 110 bucks in a millennia plus 1 year. If you give different answers for these things as you would for like hyperbolic discounting, this argument goes way out the window. Yeah.
Do our assumptions, cash out assumptions, guarantee that the system of linear equations is solvable?
Yes. This is, I won't go through the derivation of this, but yes, this is in fact always solvable with the assumptions that we've got. Mainly the fact that gamma is always strictly less than 1 is one of the key guarantees. Yeah, there's always a unique solution to this. In fact, there has to be, because each of these terms is defined as the expectation of something, which has to be some sort of number. Cool? Okay. So given a policy pi, I can compute the value of the policy pi for every state by solving a set of simultaneous equations. This is called policy evaluation. So given a policy, I can tell you how good it is in every state. If you assume the policy is deterministic, that is, instead of pi mapping from state to distribution of actions, pi just maps from state to action, then this simplifies a little bit further, because I don't sum over all the things I could have done, I just do the thing that pi tells me to do. So the Bellman equation reduces to this, where A is just whatever pi of s leads me to. And in fact, this is probably what we'll be using today mostly, because for today our policy is just going to be a deterministic lookup table that's learned. Okay? Cool? Great. So we only need to sum over all the states to find the value of each state given a policy. However, this doesn't tell me what policy to choose. I have to sort of come up with one on the spot, and we'll see in a moment where the policy comes from. So example time. Here is a cutesy little MDP. It's got 3 states. It's all deterministic. If you're in this state, you've got 2 options. You can either go to the left and get a tasty +1 reward now, or you can go to the right and get nothing, and then the next time step, you get a +2 reward. So there's, up to isomorphism, there's only 2 real policies. In the starting state, go left, or in the starting state, go right. Which is going to be better? Who reckons that going left is better? Who reckons that going right is better? Yeah. Who's the economists in the room that realized the trick question actually depends on whatever discount factor I choose? Yeah, great, you guys. Okay, so depends on your discount factor. If I'm dead in 5 minutes, then absolutely, I would rather the tasty +1 now than like hold out and wait for the future. I don't got the time for that. So exercise to the reader, you can derive that the value of the initial state with respect to the go left policy is this, and with respect to the go right policy is this, and your break-even point happens to be gamma equals 1/2, it's worth doing this derivation to get like a vibe of how the Bellman equation works. Because obviously if gamma is 0, all I care about is the next instantaneous reward, and the future is irrelevant, so of course I will go to the left because 1 is bigger than 0. Cool. Questions about this? Alrighty. I realize we're moving at a very quick pace, so you guys should ask more questions. I'm a little concerned. But. Okay, optimal Bellman equation. So we define a policy pi1 is better than another policy pi2 if for every state pi1 has a higher value than pi2. This gives us a partial ordering on policies. Yep. A policy is optimal if it is better than any other policy. Magic theorem, I won't prove number 1. An optimal policy pi star always exists for any Markov decision process. We can define the optimum value function as just maximizing the value function with respect to the policy. There has to be finitely many policies because there's finitely many actions and finitely many states. So you want like number of states to the power, number of actions to the power of number of states. So I guess in principle you could sweep through all exponentially many of them, but this like wouldn't be tractable. We need something better. Yeah, question? If you have stochastic policies, this argument doesn't work. However, if you allow stochastic policies, there still is an optimal policy. It's not unique. And in fact, for any MDP, the optimal policy is always deterministic, which I will not prove. But yeah, really. Cool. Other questions? Yes?
Like policy in this case doesn't mean strategy. It could also be like a literal one-to-one mapping.
Well, that is a strategy, isn't it?
But like if you would say greedy or so, then you could think of a case where like in this state, the greedy wouldn't be the best choice or so.
I mean, that's just like, that's rolled into your table, right? So like, I imagine I walk up to the chess tournament with this like monstrous sized telephone sized directory. And as I look up the state in my table and then do this action, and assuming you could fit that book in the universe, which you can't, I could like play chess optimally in this way. That's what I mean when I say policy. Just like a lookup table from state to action. Later on, obviously, lookup table too big. We're going to have to do some neural networky stuff to approximate the table. Yeah.
Do we need to specify a special starting state or not?
Implicitly, no. The Bellman equation doesn't require this. However, usually for MDPs that like run for some time and then end, you usually either have like this is the starting state, or you have a distribution of a starting states and where you like spawn. Yeah.
In practice, like how many steps do I walk forward in time? I mean, it's like it blows up kind of, right? Depending on how many different actions I can take and how often I want to like calculate this policy, right? I mean, it could be like I don't know 100 steps in the future, something great might happen, but I can't calculate it because it.
Yeah, implicitly the number of states has to be like relatively small to do this. There's an update rule that we'll get to that will resolve the fact even if there's exponentially many policies, we can still find an optimum pretty fast. So maybe I'll come back to that question. All right, anything else? Okie dokie. So I claim an optimal policy exists, and we can in fact write the optimum Bellman equation. This is better than before. This is just the value of the optimum policy, but instead of doing what pi tells me to do, I just pick the action that's the best. Now the problem is, this is a set of non-linear simultaneous equations, so I can't just like big map-mul inversion to find the best value function anymore. There's no clear way to solve for the value function, and I can't just sweep over all the policies because there's exponentially many. So you have to like do some clever tricks to be able to solve this thing. So clever trick numero uno. This was my optimum Bellman equation. It's just the Bellman equation, but you maximize over actions rather than doing what pi tells you to do. We note that this term here is bigger than this term here. We've replaced the optimum value with the value with respect to some policy. Obviously, whatever the value is if you do optimal things is bigger than or equal to the value if you do any other policy. And then we can replace this term here with this term here. Instead of picking the action that maximizes this sum, I'll pick the action pi tells me to do, which is like no better than doing the maximum, sort of by definition. And then this term here is exactly equal to the value of s, because this expression here is just the Bellman equation. Yes? Yeah. Questions? Cool. So why did I do that? Given the value of a policy, v pi, so you already give me the value of your policy, I can pump it through the optimum Bellman equation to get a better policy. We call this new better policy pi star, and the better policy is defined basically as this term here. Given your value, you write out this expression for every action, and then you pick the action that has the highest number according to this expression here. So the Bellman equation allows me to essentially upgrade my policy, assuming you've already got the value for it. We call this operation policy improvement. So given value, run this through, and we define our new policy as whatever action makes this expression the biggest. Exercise to the reader, you can prove that the new policy pi star is better than the old policy pi under the definition of better that I gave you on the previous slide. Cool?
This is like gradient descent for reinforcement learning.
If you squint really hard, no. We'll do something called temporal difference learning, which if you do squint really hard, it's kind of sort of gradient descent. Okay. This is more like explicitly, this requires access to the environment and the reward, which will weaken later. This is more like explicitly doing an upgrade of, I guess you could sort of consider it gradient descent, but it's like kind of tenuous, yes?
This is basically like you take a state and you like find the action that maximize the next value, and you change the equation to take that action.
Yeah, you've got your like somewhat crappy lookup table of how valuable each state is, and I upgrade my policy by, in this state, choose an action that leads to the next best state according to how I believe goodness to be. So I start with a crappy value function, I get a crappy policy, I start with a bad policy, I get a somewhat bad value function, and then I get a slightly better policy. And then I sort of bootstrap up from nothing. That's like kind of the goal here. So I don't think I would call this gradient descent.
Does it convert?
Yeah, it does. We'll get to that. Yes?
So are you picking your new policy by looking at like, okay, I know the next most valuable state that I want to be in.
Yes.
Which is the policy which is most probable to give you that state?
Yeah, my new policy is I look at my great big lookup table that's like bad estimates. In the current state, which action leads to the best state? I'll choose that action. Even if my table is kind of wrong, I'll get a slightly better policy in the process.
I choose choosing that action.
Exactly, yes. For every state, do the thing the lookup table tells me to do, pick the action that leads to the next best value according to what I believe is valuable.
So you have access like to the state and the reward function. This is basically like just picking the best policy.
In a sense, but you can't sweep over exponential method. This is a kind of like an iterative process to optimize for the best policy. But yes, it assumes access to TNR. We'll weaken that later. We have to approximate this somehow. Yes?
The proof here, is this all sort of assuming that we're going to deterministic policy, or is this what you use? Not assuming.
Here, the policy will be deterministic. You can define this for stochastic policies. The proof still goes through. It's just like more work. Yeah. No question? Okay, cool. So we put these two things together. Policy improvement, given a value, get me a better policy. Policy evaluation, given a policy, tell me the value of each state. I have something that maps from policies to values, and something that maps from values to policies. And importantly, we have a guarantee that pi prime is better than pi when I do this step here. If the policy gets better at every step, and there's only finitely many policies out there, at some point I have to get a policy that's better than everything else. This will converge to optimal eventually, which is kind of nice. So start with any policy you like, doesn't matter how bad it is. We note that pi star is a fixed point of policy improvement, in that if you take pi star and you pump it through this equation, you'll get pi star back out again. So we just alternate until the policy stabilizes. So take a policy, evaluate how good it is, and then iterate upon it. And then evaluate how good it is, iterate upon it, blah, 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 blah. Rinse and repeat until you get stuck. Ta-da, we have the optimal policy. It was just that easy. Question?
We know, someone knows that there's no other fixed points that are worse than pi star.
If a policy is a fixed point of the optimum Bellman equation, one can prove it must be an optimal policy.
Okay.
There is a little slight lie that I said here. The optimal policy is not unique in that suppose you're in an environment where it doesn't matter what you do, you always win. Then like going left is optimal and going right is optimal. However, the optimum value function is unique. So you terminate based on this rather than terminating based on pi. Cool. Anything else? Cool. Great. So now we have a way to find an optimal policy. Reinforcement learning solved. That was easy. Unfortunately, it requires access to T and R, which we normally don't assume.
You said that the value function is always unique.
For a given policy, sorry, the optimum value function is unique. Yeah, there can't be two policies that are both optimal and have the same value function.
Even for a uniform environment.
For a uniform environment, there will only be one value function.
Yeah.
So I guess everyone has that value function.
Okay.
Cool. Any other questions? Yeah. So in practice, when you like prove this thing converges, you don't consider pi, you consider like the equivalence class of all policies pi, and two policies equivalent to their value functions match. Divide out by the isomorphism, blah, blah, blah. So there's a bit more extra legwork to be done. Cool. Alrighty. Whew. Okay, here's the little itsy bitsy toy environment we'll be dealing with today. So it's a little grid world, and it's slippery. So the agent can move in any one of the four cardinal directions. If he bumps into a wall, nothing happens. If he bumps into this black square here, nothing happens. And the world ends when the agent falls into heaven and gets +1 reward, or falls into hell and get -1 reward. We also give the agent a little -epsilon on every time step to encourage him to like get on his way and not like dawdle, to like encourage him to get to +1 as fast as possible. So the other thing is the environment is slippery. So when I move in a particular direction, there's only a 70% chance I walk in that direction and a 10% chance I trip and fall and move in one of the other 3 cardinal directions. So this means that like walking past this part might be risky. You might accidentally fall into hell along the way to going to heaven. Cool. Questions about how this environment is defined? Yes?
Wouldn't gamma be enough to incentivize going there quickly?
At the moment, let's just pretend gamma is 1. Other questions? Cool. Okay. So here are the optimal policies for various choices of epsilon. So what's going on here? For very small epsilon, we only like nudge the agent a little bit in every time step. He takes his sweet time. If he starts here or here, he walks all the way around to get to heaven to avoid accidentally falling into hell, because -0.01 every time step is not that big a deal. If you dial up the punishment a bit, then the agent's a bit more risky and will happily move past hell on the way to get to heaven, because walking around here will take too long and I'll end up accruing less reward than if I'd taken the risk. If existence is suffering and you really dial it up, the agent wants to die as fast as possible, poor little guy. And if existence is bliss and you actually get positive reward in every time step, the agent will run around and bash his head into the wall and like drag the game out as long as possible. So sometimes he'll like slip and move to left, like, no, I'll go back again, and just like milk the environment as hard as possible. Yeah, question?
So the agent doesn't have the ability to choose to move off the board, but he
No.
can choose to try and move into the wall.
Yes, if he moves left here, he'll go bonk and move back again. So like deliberately bumping into the wall is like a valid action. In fact, that's exactly what the agent does right here. It just like slams his head into the wall a bunch of times, because existence is nice and I can just milk 0.01 reward in every time step rather than going to heaven. Any other questions? Yeah.
I get what it's supposed to show, but isn't it an A? Wouldn't the agent with enough experience also learn to not, or like to take the shortcut and not to go the long way?
Well, the shortcut's risky, right? So if I'm here, if I'm in this environment and I take the shortcut, 10% of the time when I try to walk up, I accidentally fall to the right. Like the slipperiness is baked into the world. So the agent learns this is a slippery, risky thing, but I'm in no rush. I only get a very slight time penalty. I'm going to walk around.
But isn't the same true for if I go the long way around, I'm exposed to more sides of this black thing?
Yes, it ends up being like more slipperiness. You might like fail to walk, but if you fail to walk, just like try again. And because the penalty is so low, it's like worth it.
Is the slippery that you just stay, or is the slippery that you can go and
You go in any one of the 3 other directions with 10% probability. So if you're here and you attempt to go up, 70% of the time you go up, 10% of the time you bump left, nothing happens, 10% of the time you bump right, nothing happens, 10% you accidentally walk backwards.
But if I walk the long way, then there are 3 states where I could theoretically go into the black square.
Yes, but if you run the numbers, it just happens to be the case that going on the long way happens to be better. Like if you just solve for the optimal policy, this is what you get. And as you tweak this epsilon, eventually the shortcut becomes better, or speed lining straight to hell is even better.
The black square isn't giving us any negative reward, it's just impossible. So if you bump into it, it's fine.
Okay.
Yeah, sorry, this is just like an immovable object that the agent can bump into, nothing happens. It's just a wall. Cool. Any other questions? Great, so hopefully your policy matches these ones here I've got when you like run your agents today. Okay, the last thing we're going to talk about is Q-value, Q-learning, which we'll interact a bit with tomorrow, and then for neural networky stuff, we'll keep it to tomorrow. So, okay, here's a big glossary of all the terms that I defined. Yes, a nice little lookup table that you'll probably be using today. So, anyone want to ask me about any of the glossary terms that I defined? All right, too late. Okay, so.
Key story and trajectory should end with a state.
I'm sorry?
Is key story and trajectory, are they ending with a state or
If it's a continuing environment, then it never ends. And if it's an environment that terminates, then I think you take an action and the world just abruptly ends. I guess it doesn't really matter whether you end on a state or end on an action, because if it ends on an action, you're dead. If it ends on a state, you don't get to choose anything and you're dead. So it doesn't really matter that much. But for today, we do continuing environments. Okay, problems. Why does this suck? So the problem is that we require white box access to both the environmental distribution T and the reward function R. I already know how the world works. This isn't very, very realistic. Also, this only works for environments with few enough states and actions I could actually hope to sweep through them. For chess, there's like, what, 10 to the 120 states? I can't possibly do this direct Bellman optimization on chess. So for the moment, I'll weaken just the first assumption. I'll assume the environment is a magic black box. States and actions go in. New states and rewards come out. I can still sweep over, I know the set of all states, but I don't know how the world works. So I can still sum over states, but I have to learn from experience rather than directly optimizing against T and R directly. Okay, so our goal is to somehow perform policy evaluation without being able to touch the environmental distribution. So here again is the value function. So the value function in state S with respect to policy pi is the expected value of the next reward plus the discounted value of whatever the next state is. That's just our Bellman equation from before. Now, on average, this is equal to the actual reward received from the environment plus the discounted value of the actual next state. This, if you squint, is kind of like a loss. And if you squint even harder, the difference is kind of like a gradient. We call this the TD error, or the temporal difference error. The temporal difference error is basically this guy should always be true. So the difference between these sides of the equations on expectation should be 0. So this is a measure of like how valuable the next state, how valuable the return is, guesstimated by the actual return plus the discounted value of the next state. So this is like my ground truth, and this is like my guess. And the difference between these two kind of gives you a gradient, inverted quotation marks, of how you should update your best guess. So I play online, I measure the temporal difference error, and then I bump the value function in the direction of the temporal difference error. If the temporal difference error is positive, that means this term here was much bigger than this term. That means my estimate was too high. If the temporal difference is negative, that means this term here was bigger, my current estimate was too low. So we take our old value function and we bump it in the direction of the temporal difference error, which is kind of sort of like a gradient descent. Cool. Questions about that? Okie dokie. Theorem, given the learning rate decays to 0 in a nice enough way that I will not go into, temporal difference learning is guaranteed to converge to the optimal policy, which is, guaranteed to converge to the value of some policy pi. If you fix a pi, this will tell you the value without knowing how the world works, asymptotically. Cool? Okay, I'm going to talk about this thing called Q value, then I'll wrap up in a few more slides. So the Q value, as opposed to the V value, is the expected return in state S, take action A, and follow policy pi. So recall that the value function is in state S, what's the future discounted sum of returns following pi. This is slightly different. This is in state S, force some action A, and then afterwards follow pi. So if A is derived from pi, these two things are equivalent. And if they're not, this is forcing an action, and then afterwards I do whatever pi tells me to do. Exercise to the reader that I won't go into. We have a Bellman equation for Q, an optimum Bellman equation for Q, in the same way that we have Bellman equations and optimal Bellman equations for V. You derive this in exactly the same way that I did the derivation before. Question? Cool. One can state Q in terms of V and V in terms of Q. I won't go into this. And then why do we care? We'll be learning a policy pi and using pi to compute V. Now the problem is, if I hand you the optimum value function on a silver platter, this is not useful. It doesn't tell you how to play the game. If you're playing chess and Magnus Carlsen comes over and says, mate in 36 moves, so what? I don't know what moves lead me to get there. That's the problem, right? I don't need just a lookup table of the value of each state. I need to know what actions I need to take to get there. If I know this state is like a winning state, that doesn't tell me how to actually win, right? It just tells me the state I'm in is valuable if I knew how to play optimally, which I don't. So given the optimum value function, you can recover the optimum policy only with access to T and R, which we assume that we no longer have. However, if I have the optimum Q value, the Q value is just a dirty, great big lookup table of how good is every state action pair. If I have a lookup table for every state action pair, given a state, I just look at my lookup table, and then it says the value of each action, and then I pick the action that's the best. So I can just argmax my Q value table, and I can recover the optimum policy, assuming I had Q. Yes?
Can Q be seen as like an average across actions? And that, can V be seen as an average across actions of Q?
Can V be seen as an average of actions across Q? Yeah, I mean, if we jump back to the previous slide, we can write the value as, in terms of the Q, with expectation with respect to both the policy and the environment. And if the policy is optimal, then V pi S is just Q pi SA, but A is always whatever the optimum strategy tells you to do. Cool. So So the idea is we learn the optimum Q value, and then we argmax that to recover the policy. We're about almost an hour, so maybe I might wrap up at this point, continue the rest of the talk tomorrow. So I'm going to pause here, do some questions, and then we'll wrap up for today. Cool. Now ask me some questions. Maybe I'll put the glossary slide up in front of you, so this is maybe a useful thing to have. There we go. Okay. I said a lot of words. You should ask me questions about them.
Can you explain again what is the V value function
The v-value function, great. So the v-value function,
No, sorry, not this one. The one that you explained afterwards.
the q-value function,
No, the Q value I understand it. Go on.
There's only two, there's me and you.
tell me when.
No, sorry. I think I missed that. Yeah, I don't know.
All right, well, come back to me. Anyone else I'll jump back to the glossary slide. I know I said a lot of words. You will have these slides in front of you, and I will be helping you through the day, so don't worry. But this is 3 chapters of a textbook in an hour. Cut me some slack. So, other questions? Yes?
What's the enough intuition for why RL is harder to train? Just jumping. Is there an intuition for that?
The intuition is that you only get scalar feedback. So rather than gradients. The LLM predicts a bunch of tokens. You get exact feedback on, no, here's the distribution you should have given me. Here's the token you should have guessed. Here's the negative log likelihood you assigned. You compute the loss. You gradient descent against this. Here, it's you might generate an entire paragraph of text, and the reward function goes, boo, you suck, and that's it. You get no other feedback. You just got to work it out. So that might be why RL is difficult, right? Imagine you were trying to, learn how to speak as a child, and all you got when you say something is the carrot and the stick and nothing else. You don't get to mimic from your mum or dad. That's it. It would suck, right? It'd take a long time. That's one reason why RL is, in general, very difficult.
I think there's other reasons why RL can be annoying.
Yeah. In practice, you could have everything set up correctly, and you train it, and it just falls over anyways. RL can be a very finicky beast and very difficult to tune. Transformers really want to learn to predict the next token given gradients. RL, you can just things you just fail for no reason because training is unstable. You have no ground truth to chase. Things are very messy. We'll talk about this more when we go to DQN tomorrow. All right, other questions? Yes?
You can explain it in an hour. Why is there 3 chapters in the book about it?
I don't know. Did I do a good job of explaining it in an hour? Oh, well, there we go. I don't know. Because presumably if you sat down and read this at a much slower pace, it might internalize a bit better than me rapid fire talking to you very quickly. Yes?
You said carrot and stick a lot of times, but in a sense, I guess a big chunk of the task is to write a good reward function that is not so sparsely, I guess.
Yeah, at no point have we even talked about the reward function. We just assumed it was handed to us from God. But if you want the agent to learn to do a backflip, you're going to define your own reward function. That's its own problem, right? So yeah, there's difficulties there too.
Reward shaping, right?
Mm-hmm.
Kind of almost like an early version of the alignment problem.
Kind of, sort of. So for those who don't know, reward shaping is trying to learn how to play chess, +1 if you win, -1 if you lose. Wow, that's very difficult. So maybe give a little bonus reward if you capture a piece, and a little negative reward if you get a piece captured, and a bonus reward if you take some territory, yada, 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 yada. The problem is sometimes the agent can overfit and then focus just on the proxy rewards and just capture pieces even if it means it loses the game downstream. So reward shaping has its own problems as well. RL, very tricky. All right, maybe one last question, we'll wrap up. Yeah.
What are kind of the key parameters to tune, or to optimize for? So there's certainly the discount that we kind of set.
The discount, at least at this framing, I would say the environment, the discount is fixed, optimized with respect to these 2 parameters. Now, if you have some particular behavior that you want, you might tune the discount factor so the agent learns faster or slower. Lower discount, learn faster, but suck. It's a very myopic, it's a short-sighted agent. Very high discount factor, the agent is more long-term, seeking into the future, but learning is slower. So
Okay, but if the discount is fixed, then it would be the epsilon and the reward that are up to 2.
If you're learning, if you have access to the environment, you just solve directly with policy evaluation, policy improvement. If you don't, and you're doing temporal difference learning, which we'll kind of maybe touch into today, maybe tomorrow, depending how fast you go, then you tune the learning rate, or tune the exploration parameter epsilon.
Can epsilon or any of those things change over time?
Yes, but that's an architectural choice on you, not something to do with the environment. Okay, last one. Okie dokie, we're at an hour. Let's wrap up, I think.